All right, let's talk some about water balance. Whenever we, in earth sciences in general, have a balance equation, we're usually referring to this equation. Inputs minus outputs are equal to the change in storage. And we can express this symbolically by saying I minus O equals delta S. When we look at a catchment, what are the inputs and outputs? Well, they are precipitation is an input, precipitation, minus the outputs. One output going back, the return of water vapor to the atmosphere, is evapotranspiration. And this is either from the surface of leaves, transpiration, or abiotic evaporation. It's the combination of both. And then the other output we have is runoff, or discharge. And so this is equal to the change in catchment water storage. Let's denote this with a P. This is ET, and this is Q. Now, this particular equation for catchment mass balance assumes something. Namely, this assumes that there's negligible groundwater inflow or outflow from the catchment. Which is an assumption that may hold in some places, but may be a very bad assumption in other places. So I'll say there's negligible groundwater import or export. So we're just looking at surface water runoff as the main flow of liquid water out of the catchment. So let's cast this in terms of a conservation of volume equation. And we can either conserve mass or we can conserve volume. Because liquid water has a fairly uniform density, at least in terms of our ability to measure these fluxes across typical Earth temperatures, we're just going to assume that we can interchange volume and mass. So 1 liter of water is equal to 1 kilogram of liquid water. So in this particular equation, let's conserve volume. So if we're doing that, we have the following. We've got precipitation, and as we mentioned previously, the dimensions of this are usually a flux, length per time. So to get this into a volume, we need to multiply by A, the catchment area, the area over which this rain is falling or snow is falling. It says dimensions of length squared. And then we still have a time here, so I'm going to multiply this by a little time step, delta t. This now has the dimensions of length cubed, which is volume. We'll subtract this from ET, and we need to do the same thing here, A times delta t, because ET is also typically described in dimensions of length per time. These capital letters denoting the dimension. And then finally, Q. Q is often measured in terms of volume per time, the amount of volume flowing in a stream per time. And so it's already kind of got these dimensions of volume in here. And so we're just going to multiply it by delta t. And together, these will equal the change in storage S, which again, because it is a volume, just has units of length cubed. If we were to factor out the A from this equation and then divide through by the delta t, we'd get the following. A times P minus ET minus Q is equal to change in storage per change in time, delta t here. Now, what I would like you to do is recall the definition of steady state. And at steady state, we know that the input rate into the catchment is equal to the output rate. Input rate equals output rate. Because the input equals the output rate, we know that these terms all cancel out. And so delta S over delta T must be 0. There is no change in storage at steady state. When we're at steady state, we can calculate the average residence time of water in the catchment. So the average residence time I'll denote this with a tau, is equal to the volume of the reservoir divided by the input, or because it's equal, the output rate. And there's two ways that you can get some intuition if you have trouble remembering the definition of residence time. One is that if you have a really big volume of reservoir, this term's going to be really big. And if you just have a small trickle in or out, you can imagine that residence time should be pretty large. So you're going to be dividing the volume of the reservoir divided by the input or output rate. The other way that you can remember this is to appeal to dimensional analysis. So you know residence time should have dimensions of time. So what do you need to divide? What do you need to put in the numerator and denominator in order to get back to dimensions of time? Well, the volume has dimensions of length cubed, and the input or output rate has dimensions of length cubed per time, such that when you divide these, the time comes back on top and you get back to where you're supposed to be. So that's one way that I remember the definition of residence time.